So tell me everything you know about transformers. Well, that's a big misconception. Transformers do not change power. Power in, if the transformer was 100% efficient, power in would equal power out. You understand that? Transformers do not change power. Power in equals power out, right? You understand? And the way I explained it at class, if all our transformers were 100% efficient and I turned on a 100-watt light bulb at my house, then the power station would give me 100 watts. And that's why they sell you power. They sell you power, right? Because power is work, right? We're just able to deliver that power at different voltages. So what does a transformer do? Voltage. But current, you got to understand, if it steps up voltage, what happens to current? It goes down because we're delivering power to a load, right? And of course, what we're trying to do, if the power is equal to V times I, then of course I would be equal to P over V. And that means the higher I can make that voltage, the less current is going to be required to transmit that power to your house. Now, why do we want a lower current? Well, you're getting quite a bit into your house. Alabama Power might not give you. What's the problem with current? Well, the problem with current is everything has a resistance. So we don't think about a wire having a resistance because we're not doing miles of it, right? You understand? But every wire has a resistance, right? You'll understand that. So if your battery cable had 1 ohm worth of resistance, you couldn't even start your car. But look at the size of your battery cables. They're really, really big because they have to handle a lot of current. If you put current through resistance, you get what we call a voltage drop. V is equal to I times R. So every wire has a resistance. Right? So understand that. We can't measure, but you take that 22 gauge wire, and if you had 1,000 feet of it, you measure across that thing, it's going to measure over 20 ohms for 1,000 feet. Now, over here, you're using that, but 1,000 feet is nothing to Alabama Power, right? Alabama Power is not talking feet; they're talking what? Miles. So if that wire had 1 ohm of resistance, over a mile, then if they tried to send what? If they tried to send 120 amps, it would drop all the voltage. So what they're trying to do is they're trying to get the current as low as possible, so they can get it through those wires, right? Without having wires as big as me, right? You understand that? Sure, they could get it down here, and that was the problem they had with DC. When Edison first came out, he created, so there's a big difference between DC and AC. DC was discovered, right? You understand? AC was created. So AC was invented. AC doesn't, well, it does. Electric eel generates some AC, but we didn't even know it then. So Edison was trying to wire the first house, first city, I think it was Chicago. He was trying to run power around there. And he was using wires about that big, and they had to have a power station every mile. Because why? They couldn't get that power over that line without having a bunch of power loss, right? You understand? So what can we do with AC that we can't do with DC? With transformers. If I put DC into a transformer, it'd be like a short circuit. It'd burn the transformer up. DC. So what's required to produce an EMF using magnetics? What do we need? We need a magnetic field. We need what? We need a conductor. Well, DC generates a magnetic field, and we can run it through conductors. But one thing we don't have, why we can't induce a voltage with DC, is it does not have relative motion. AC has relative motion. So AC looks like this, right? You understand? So here, it goes up to a maximum, stops up, reverses polarity. So that means if I have a coil of wire, the magnetic field builds out, and then what does it do? Then it collapses and goes and builds up the other way. So the wires, the magnetic field on that's constantly doing this. So what determines the amount? What determines the amount of EMF I can produce with a magnetic field? I think I'll go and put this on the test right now. This is very important. Understanding what this does. So what determines the amount? I guarantee it's going to be on the next test, and it's not going to be on the review. What determines the amount? Write down the list. What about the magnetic field determines the amount? Strength of the magnetic field. Number 2, conductors. What has to deal with the conductors? It has nothing to do with the size of the wire. The size of the wire determines how much R the generator has. The R determines how much current we can get out. So if I took my 10 megohm meter and put it across a 20 gauge wire, it would give me, if it had the same number of loops, it would give me the exact voltage that 2 gauge wire would give me. So what the size of the wire determines is not how much voltage is trying to be produced. It determines how much current we can get out of that generator. What determines the amount of EMF would be the number of conductor loops. And number 3 would be the speed of the motion. And I didn't start up the camera. I did have it plugged in. The diagram. Where's my PowerPoint? Can y'all see it? I'll draw it up here on the PowerPoint. These should be the same. And all we need to do is draw the primary. This would be X1. This would be X2. I'm sorry, H1. I said it right. I drew it right, but said it wrong. Over here, I said it wrong and wrote it wrong. This would be H1. This would be H2. This would be H3, and this would be H4. So that means if I was going to wire it for low voltage, or divide by 2, then what would I do? I would put a jumper between here and here, and I would put a jumper between there and there, and I would bring my AC in like that. Now they're in parallel, right? So if I drew this out, oops, I have H1 connected to what? H3, and then I have H2 connected to H4. But notice I don't have, if it's wired like this, I don't have to cross any wires. If I wanted it to wire it for high voltage, I divide by 4, I would put the jumper right here. This is the transformer right here that goes on our sensor trainers. They've already wired it for us. So notice they have a jumper. There's that metal tab right there that they come with the transformer. And they've got that metal tab going between H1 and H3. And they got it going between H2 and H4. If I wanted to jump it for high voltage, I would pull off one of these. I'd put it somewhere where I would lose it, and I'd move one of my jumpers right here. And that's why they cross those things, so I can wire the transformer for high voltage or low voltage by using these jumpers instead of me having to run a wire, right? You understand that? So that's why they cross. X2 and H2 and H3. So what we're going to do in our lab is that we're going to get inside the disconnect. So y'all get y'all's lab book out. Oops, no symbol, Rich. I'm thinking overload, but it's not overload, it's a fuse. There's a crumb of that, isn't it? This is the L1, L2, L3, and then we have ground over there. We're not on this. So what that means is, if I measure between L1 and L2, first of all, this is going to be all of us have done that before, where you squeak instead of sneeze. I don't know the symbol for a key switch, but this is the key switch that I have up to. I don't know which one this goes back to. This is a wiring diagram, right? So what we have is inside there, we got a relay. This is our, this is my key button switch right here. So as long as your E-stop is not pressed, I can come over here and take my key and turn it, and then it'll energize this relay. The relay will do what? Seal in, and it's going to close all of these contacts right here. which is going to put power out to our L1, L2, L3. I've probably got my feet on the connector. Is that okay now? Huh? So this is the E-stop circuit right here. We got a relay in there. We have an E-stop relay. This is the E-stop button. It latches. Ours don't latch down, in fact. But what happens is I come over here. Your E-stop is pulled out, which is going to seal it. I hit the key switch. It's going to energize it. Then I can turn it back, right? So all I'll do on the key switch is I'll just turn it. I'll energize it. It closes these contacts right here, and it's going to bring L1, L2, L3. These are 10 amp fuses. So one of the first things we're going to do is we're going to get in here, and this should measure. We said 120, but we're on a Y connection, which don't mean anything to y'all right now. So we're getting 208 out, or around 208. It's usually around 210. So we should expect about 208 when you measure with your meter between here and here. Between any two phases, right? It should measure the same thing. Are you okay? If you measure across the fuses, what should you measure? What? So how much resistance does the fuse have? How much resistance does the fuse have? How much resistance does the fuse have? Huh? Okay. It does have a little bit, but we can't measure. So if we have no current, and it wouldn't even make any difference. So if V is voltage drop is equal to I times R, then voltage would be equal to no resistance, I times 0. So what should we measure across a good fuse? Should measure pretty close to 0 volts across a good fuse. Even if the circuit's operational, you're going to measure a little bit because a fuse has to have resistance. That's the way it blows, but it's going to have very little, right? You understand? It's going to drop very little voltage relative to how much you have. Now, if we come over here and measure between L1 and measure here, it should be measured 208, but it should always also measure 208 on that side because it's not dropping any voltage, right? You understand that? So what we're going to do is, and then what we're going to do is we're going to come in and you're going to get me to come over here and I'm going to simulate a blown fuse. So what's that mean? What does that mean? Well, when I measure between here and here, and it might be the middle one, I can pull out any of it. If we measure between here and here, it's going to measure real low, right? It's going to measure something because it's AC. AC induces voltages and everything, right? You understand? But it's not going to measure 208, right? Everybody understand that? Okay. And then if I measure between here and here, it should measure, not there. Yes, I know. Thank you. If I measure between here and here, it should measure okay. Right? Everybody okay? So one of the first things we're going to do is we're going to open it up. I'm going to open it up. Make sure you got your gloves on, right, and safety glasses. You got to have your meter. I think the first lab that we do on the power lab is to come in and actually measure our disconnect. Then the next thing we're going to do is we're going to hook up our transformer. And you can see we've got the jumper wires over here on the right. This is where they're supposed to stay at, guys, by the way. And then we're going to come up here and we're going to hook our transformer up. With power off, right? And we're going to hook ours up. We're going to do ours a little different than what the lab book says because I want you to see the division ratio on this. And the first thing I think we hook it up for is divide by 4, I think. Now, technically, what you should do is that everybody in here, we should rotate on which L's you connect. So I should have 208 between L1 and L2. I should have 208 between L2 and L3, and I should have 208 from L1 to L3. Technically, what we should do is everybody should use a different set of L's, right? So that way we're going to balance our load. Everybody understand that? Okay. So some of y'all might wire your transformer between L1 and L2. Some of you can do what? L1 to L3, and some of y'all can do what? L2 to L3. And that's why on your house, you know, you got 240 across the outside, even 120. When you put breakers in, you're supposed to go back and forth. You're not supposed to fill up one side and then do what? Fill up the other. If you do that, you're going to put all your load on one side of your transformer, which is not good. So we'll come over here. We'll have our transformer. Our dual voltage transformer. And you saw the numbers. This is what? H1, H3, H2, and H4. And of course, if we wire it for low voltage, what are we going to need to do? We're going to hook them in parallel. How do we do that? We just take a jumper and go from here to here, and from there to there, right? You understand? And then we would bring this in, we would bring our power in here between them. Everybody okay? And then when I measure over here on this side, and this is going to be unloaded, guys, so this means it's going to measure a little high. They call this HF, and they call this X2. If over here, if we measure 210, then what should we measure over here? Huh? If it's a divide by 4. No, I'm sorry, divide by 2. Should measure about 105, right? We're okay? Everybody okay? Now, this is the way we're going to run our transformer the whole time. So when you get through with the lab, this is the way I want you to go back and hook it. This is the only thing that'll stay wired the whole semester is your transformer, right? And that way we don't have to worry about you screwing it up and wiring it backwards. It's not hard to tell. If I look up there and look at those jumpers up there, I should never have any crossing wires, right? You understand that? If they cross, it means you got it hooked up wrong, right? Everybody understand? And that's why they swapped. That's why they did the X2 and X3 like that. What we're going to do is we're going to also hook ours up for high voltage, even though it's not going to hurt the transformer. I just want you to see it work. So what I'll do is I'll just move it over here. So you start off hooking it up as divide by 2, then you'll end up hooking it up by divide by 4. And when we hook it up divide by 4, what are we going to measure out if we put 210 in over here? What should we expect to get out? About 53 volts? Yeah. Right, okay. We're going to wire ours just so you can see the division ratio on the transformer. So I want y'all to do that. And like I said, the correction book will be over here and it's going to tell you not to skip over those steps. Okay, so what's the next lab? The next wired lab, not the next homework lab. That's the one we just got to talk about. Okay, so what are we going to do here if we start looking at this lab? I need to go get my lab book so we can. These are going to be fairly simple circuits. We're not going to have any relays in them. All we're going to do is we're going to have push buttons and lights. So we'll use our light panel, use our box. It's got two lights in it, right? It's got a red one and a green one. They don't specify which light you're going to use. And then we got two push button stations. We got one that's got a normally open and a normally closed. Then we have another one that's got two of them that you can wire the way you want to wire them. And this would probably be the best one to use. So this is our indicator light and selector switch. We're not going to be using our selector switch right now. We have two lights to work with. Don't worry about the legend plates on there. They're just there to demonstrate what a legend plate is. If we look at the electrical wiring of this thing, then of course I can use 1 and 2 for a light, or I can use 3 and 4. And these are the manufacturer numbers down here. Everybody okay? Okay, any questions there? Now this is the push button station you need to use right here, because the other one, all it's got a normally open and a normally closed. This push button station right here, you got two push buttons that you can wire as either normally open or normally closed. You're the one that figures that. So if I wire between 1 and 2, I get a normally closed push button. If I wire between 3 and 4, I get a normally open push button. Everybody understand that? So we got two push buttons on here. This one they got labeled forward and reverse, that you can either wire these for normally open or normally closed. So for your ands and your ors, you're going to use normally open, right? You understand? For your nans and your knowers and your nots, you're going to use normally closed, right? You understand? Everybody okay? Any questions there? So what's our first one? So I'm going to put this up here at the top. So what's it got? It's got a normally closed between 1 and 2. And it's got another normally closed between 5 and 6. And then it's got a normally open that works off this same operator between 3 and 4. And then it's got one here between 7 and 8. And then it's got a normally closed, which is 9 and 10. 9 and 10, Rich. So what's our first circuit in that lab? What are we going to wire? Huh? Yeah, but we already showed you how to do that, right? Are we inside the logic one?
Yeah.
The first one is and or or.
And or logic.
Okay, but it's the first one's going to be and, right? Or is it or? The first circuit you're going to wire.
It says and or logic.
That's the name of the lab, but then get to the circuits you're going to wire.
And.
You're going to wire an and, right? Well, no, you're going to say connect the circuit shown in. Now that's probably right. Connect the circuit shown in figure 8. So this is the circuit shown in figure 8. So this is the first one we're going to construct. So LD8, procedure step 2 says what? connect the circuit in figure 8, right? So figure 8 is an AND, right? So everybody understand that? Yes or no? So what we got is we got our transformer. X1, X2, H2, H3, H4. This is going to go back over to either, it's up to you, right? L1, L2, like that. And we got our secondary side. The fuse side is going to be our our control L1, and then X2 is going to be our control L2. And then we're going to come down, we're going to connect to this guy, right? You understand? Then we're going to go to a normally open push button. Then we're going to go to a normally open push button. And then we're going to go to a light, right? Everybody okay? So what I'm going to do is I'm going to start assigning manufacturer's numbers. So up here I might put 1, 2, right? And then over here I might put what? 5, 6. 3, 4 is the, not 5. I put the 7, 8. I said 3, 4, put 1, 2 up there, did I need to watch out for it. 3, 4, 7, 8, and then on my light, I could, if I use the red one, then I'd put 1, 2, 1, 2, good gracious. Yeah, I know, but 1, 2, and then I run the wire back up to X2, right? Everybody understand that? So before you wire it, what you're going to do is you're going to assign the manufacturer numbers, right? You understand? And then, of course, we're going to wire this to divide by. This is going to be wired to divide by 2. Don't forget to do that. If you don't put those jumpers up there, you're not going to get anything. You're not going to get anything, right? You understand that? Right. Make sense? Everybody okay so far? So here we have normally open in series. That's an AND. What's the next one? Any questions on that? Ask now. Yeah. Okay. For OR, we're going to turn around and wire them in what? Yeah, we're going to wire them in parallel. Guys, and I don't know why people see it this way, but 1, 3, and 4 are not jumped together. There's a switch between 3 and 4. But for some people, for some reason, people want to see to put a jumper across the push button, right? You understand that? But so we come directly off of XF, which is on our, we come directly off that, we'll hook it to 3. Then we'll take a jumper and put it between what? 4 and 7. You got to put a jumper there, and then we're going to hook the light bulb to 8, from 8 to 1, right? And then from 2, and this wire right here run back to X2. You understand that? Yes?
Right there, you got X1, H2, H2, H4.
Yeah, I know. What's this supposed to be?
H3.
3, yeah.
Is that supposed to be H1 or is it
Supposed to be H1. And then the fuse is called what? XL. XL. And then your unfused side is called X2. X2, X1 is considered to be the power side, and then CL2 is considered to be the common. So that's why you'll fuse, if you got a fuse, if you got one fuse, you'll see it in CL2. A lot of industry will fuse both sides. Any more questions? Yes, no? So the next one is what? It's an OR, right? So that means we're going to connect our switches in what? Parallel. We're still using normally open. So I'll come over here, I use a normally open, right? 3, 4. Then I'll come down here and use a normally open 7, 8. So I have to laugh at myself. 7, 8. And then we'll come over here and then we'll put a light. 1, 2, or whichever one you decide to use. So you're going to take a wire, you're going to hook it up to this terminal right here, right? You're going to put it down, then you're going to come into 3, then you're going to put a jumper between 3 and 7. I don't want to see 2 wires running all the way up to the power side, right? You understand what I'm saying? So when we draw them in 90-degree angles. Straight lines are 90-degree angles. But when you wire these things up, you'll look like this. So you'll come over here and you'll have, I'm just going to use a different color wire. You'll come over here, you'll bring this down, one wire, you'll put that in there, right? And then you'll jump it from here to there. So that's the way that will be wired up. That make sense? And then you'll come over here and you'll put a jumper between 4 and 8. And then it's up to you whether you want to come out of 8 or you want to come out of 4. It don't make any difference, whichever one is closer. And then we'll jump over here. And then then this will come up and go back up to there. Now that's the way it's going to be wired, right? Does that make sense? That's not the way we draw it. So when we draw them, we use straight lines, even though mine wasn't straight. It's hard to draw on a display that's bouncing. But they're going to be straight, and all we have is 90-degree angles. If we want a connection point, we put a dot out there, right? You understand? If you don't put a dot, what does that mean? It means it's not connected, right? Everybody okay here? Any questions here? Okay. So that's the first slab, right? You understand that. Then the next slab in this section is what? And, nors, and nots, right? So ands and ors are what's required to make the rung true. So here we have, let's say I can press my first one or my second one. So I can press the one between 3 and 4 or 7 and 8 to turn the light on. For nands, nots, and nors, it's going to be what's required to turn the light off. So these rungs are going to be true. So you get over on your nots and your nands and your nors, as soon as you throw power on that thing, that light should come on. Everybody understand that? So what I'm going to do now is I'm going to shift over to what's the first one? Nor or nan? It's not? Okay, so we'll come over here. We'll have a push button, normally closed. And I'm gonna come over here and I'm gonna put a light bulb up here, and I'm gonna take this back to. Should have this down here. Of course, my normally closed. You can use the normally closed. It's up to you. We do have a normally closed from 9 and 10. So you could use 9 and 10 if you wanted to, or you can use 1 and 2, or you can use 5 and 6. Because all we need is one push button. It's up to you. Are you okay on this one? So now, as soon as I come over here, I'm going to come over here. By the way, all I'm going to do when I come over there, it's going to say, have the instructor apply power to your circuit. So don't ever skip over that one, right? Skipping steps is bad in this class. If it says have the instructor apply power, you're going to get me to come over there, right? You understand? I'll come over there. I'm going to check the L2 side, the CL2 side. If it's right, it means there's no short circuit. It don't mean the circuit's going to work. It means there's no short circuit, and that's all I'm depending on. Then what you'll do, if I see no short circuit, I'll go ahead and put power on your circuit, and I will walk away. It's up to you to determine if the circuit's working the way it should be. What we should see here, though, as soon as I turn the power on, that light should come on. Because nots, nans, and nors are what's going to be required to make that light go off, right? You understand? Ands and ors are what's required to cause the light to come on. What we should say is ands and ors is what's required to make the rung become true. Nans, nots, and nors are what's required to make the rung become false. So everybody okay on this one? Y'all gonna have any problem with this one? Very simple circuit. We usually go through these fairly fast. What's next? A NOR. So what's a NOR? In series or in parallel? Series. And of course, we're only going to be using 2, but you have to understand we could put a lot of them out here. We just don't have enough push buttons. So here we're going to have to switch over to the normally closed. So here I might want to use a 1 and a 2 on the other one, and a 5 and 6. Then where's the other light at? I think it's just right down the line. 3, 4. The light. Of course, I didn't need to draw a dot there because there's nothing in parallel. And this will be our 2 push button NOR, right? So it says any push button pressed will cause the run to come false. And then what's the last one? NAN, right? And they're going to be hooked in what? And y'all need to know that. This is going to be on test. But they're normally closed in parallel, right? So the labs, any questions on this? Okay, everybody in here okay? Yes, no? No question?
That's true. So on the light, put 3 and 4.
Yeah, that's the second one.
Okay.
You got 2 lights to choose from. You don't have to ask. That's why I changed this one up. Okay. We got a green light and we got a red light. So it's up to you which one you use. By the way, don't pay any attention to the legend plates, right? They just showed y'all that way. So out in the industry, just about every push button is going to have some type of legend plate on it that tells you what it does. So those are just on there for demonstration. But we have people in the class who come in here, they don't want to use it because it's got forward on it. And forward is a relative term anyway, right? So yeah, this is the other light. So this would be 3 and 4 is the green one, I think. Yeah, 3, 4 is the green one. So what are we going to be using? We're going to have our transformer. We're going to wire it for low voltage. So when you get through with the lab, on the wiring the transformer up, it's going to be wired for high voltage. And remember, you should measure around 50 something volts out of it, right? When you get through that lab, I'm going to say, okay, you need to rewire it for low voltage, or divide by 2. Yeah. And then you'll come to this lab. Because you put 53 volts across these light bulbs right here, you're not going to see them even glow, right? You understand? Because there's not enough there. Y'all know that the power varies with the square of the voltage. Y'all understand that, right? So if you put half the voltage on the device, it's going to try to produce 1/4 of the power it was designed to do. So, you understand why? Well, P is equal to V times I, right? I is equal to V over R. So if you double the voltage to a circuit, now we're not talking about from the source, we're talking about to the circuit. If you double the voltage, this is going to double down here. It means your current's going to double. So if power is equal to V times I, if you double the voltage to a circuit, you double the current in the circuit, so it varies with the square. So if you put 3 times the voltage on there, the power that is going to try to produce 9 times the power. If the voltage goes down, it's 1 over the square. So if the voltage goes above what the thing is rated at, it's the voltage squared, right? I mean, not the voltage squared, it's the power squared. If the voltage goes down from its rated value, then it's going to be 1 over the power squared. That's not true. I was right. It's not the power, it's just the square. So it's not the voltage, it's the voltage increase. So let me make sure we understand that. So if you double the voltage, then this is not the voltage squared, it's how much the voltage increased squared. That makes sense? I don't know how, so it's the voltage increase squared. So if you double the voltage, the power produced by the device will try to go up 4 times. If you triple the voltage, it's going to try to go up 9 times, right? You understand that? So this is why common loads are designed around a certain voltage. So that means you go out and buy a light bulb. I don't care if it's LED or something. It's going to tell you what voltage you're supposed to run that thing on. If you try to run it on a voltage that's too low, it might not even come on. It's consuming power, but it's not putting out enough power for you to see it, right? If the voltage goes up too high, then what's going to happen instantly? It's just going to burn it up, right? So we're going to do that on purpose later on in a troubleshooting. We're going to put a voltage across a light bulb that's a lot lower than what it's supposed to be, and the light bulb's not even we can't even see it come on. But it's doing what it's supposed to do. So this is the first 3 labs. So I think this is the lab on power. So we're going to measure inside the disconnect. Got 208 volts in there, guys. Make sure you have your gloves on. Make sure you keep up with what you're doing, right? You understand that? I'll have to come in and that big silver thing that's got a triangle in it, I'll open up the disconnect. And then it's going to tell you to pull a fuse. I'll come up with disconnect. I'll pull a fuse. I'll try to find my fuse puller. If I don't have it, I'll just have to figure out another method. I don't think I brought it over. But like I said, this is not one of the classes that I usually teach anymore. Mr. Sanders is basically teaches this class now. But any questions on this, right? Y'all, now's the time to ask it as a class. Y'all need to.
Hey, go ahead, real quick.
On the light blue part, are the manufacturer.
That's the manufacturer. Yeah, off the panel. Yeah. So we come over here and projector's still up. And somebody wrote on this one. Y'all don't write on any of this stuff, right? That makes me so dang mad. We had an instructor that had some trainers, and he got a permanent marker off and wrote bad on a trainer. Like we can't fix them. I mean, we've been doing that for a living most of our life, fixing stuff that breaks. And he got a permanent marker and wrote bad across the trainer. I got so mad. So could y'all see the manufacturer numbers up here? See where somebody wrote up there? Don't do that. So I've got two options. It says the red light is between what? 1 and 2, and the green light is between 3 and 4. And then here's the selector switch. We're not using selector switches right now. And then of course here's the push button station that we'll be using. Like I said, we got 2 push button stations, but the other one, you got one normally open and you got one normally closed, and that's all you got. This one, you got these 2 right here that you can wire them as either what? Normally open or normally closed. So these are the ones, this is the station that we'll be using. So the other one is kind of like this one. This button right here, you've only got one option for that one. It's a normally closed push button. And momentary contact, you understand that now, right? So what you're going to have to do on these, you're going to have to do what? You can't push this one down and then push that one down. If you want to make them both true, you got to push both of them down. If you want to make them both false, you got to leave both of them up. But you need to also check. You're going to go through the function and make sure that that a NAND says all to be true, right? Any questions?
On the look in the H1, H3, H2, H4. So to be, when you hook H1 up by itself and you just hook H3 and H2 up, and H4 by itself, that's for high power hookup.
If you go from H2 to H3, that's for a divide by 4. Not high power. Transformers do not change power. There's no such thing as high power and low power. Transformers change the voltage, which in but it also changes the current. So if it steps the voltage up, the current's going to go down, right? You understand? If it steps the voltage down, the current's going to go up to provide the power. So transformers are the source. You know, you say, well, in DC we learned if voltage goes up, current goes up, but that's talking about the load. If you change the load, right? If you change the voltage to the load, we're talking about the power source. What's going on in the power source that's getting power to those loads. And that's right. If you increase the voltage to a load, current's going up. If you decrease the voltage to a load, the current's going down. But on a transformer, that's the source of the what? Of the power. And they're called power supplies, you know.